there's a sort of subtitle, which is that one of the ingredients I'm going to use to do this is constant depth Clifford circuits, which if you're interested in forming Clifford circuits might be a useful thing to know that you could do. Okay, so we often want to implement some non-unitary operations on our quantum computer, even though the sort of most natural operations are unitary gifts. And the sort of most obvious one is the one that's very prominent in physics and chemistry, the Hamiltonian of some system. And here I'm assuming we've been given a Hamiltonian as a sum of terms which contain these omegas, which are complex coefficients, and these ULs, which are some unitary. We can input some version of this Hamiltonian into our computer in a variety of ways. But one particular way is to use a so-called block encoding, where we have some larger unitary where only one corner of it encodes this non-unitary pitch, which may include some scaling. So it actually can be put into a unitary, but I'm going to ignore the scaling of this talk. So we have this Hamiltonian, and we want to block encode it. What's the canonical way of doing this? The usual way is this linear combination of unitaries, LCU technique. And this usually involves two ingredients. They're called prepare and select. The prepare circuit simply loads these coefficients into a register along with some index. And the select circuit takes that index and applies the unitary corresponding to that coefficient onto your state side, which is just whatever state that currently corresponds to your system.
And the lambda is the scaling factor.
Yes, the lambda is a normalization factor. It's the sum of the omegas. Yes, of the norm of omegas. Yeah.
These omegas could be complex.
Yes.
Yeah.
Omegas are complex, although in many cases they're just. But yeah, they can be complex, and if they are complex, what you usually do is you absorb the phase from them into the ULs.
Does that stop that being used? You absorb that phase.
No, I think you can always.
Yeah, so I think you can always just choose them to be real by absorbing phases. Yes.
Do you also make them positive in that way?
Yes, you can always make them real and positive.
Yeah. So you essentially take out the computation.
Yeah. Feel free to answer.
Yeah.
But most of this talk is going to be concerned with circuits of this select form. So what are these circuits doing on a basic level? I mean, the circuit, if you were to actually draw out the circuit, you'll find out in this sort of quite like circuit diagrams. If you actually look at what they're doing, they're just saying for the index that's 0, do this unitary. For the index that's 1, do this unitary, etc. Go through all of them until you've applied all the unitary group coefficients. To kind of motivate why I sort of started doing this work, I'm going to show you I'm going to talk to you first about a kind of special case of that particular circuit I was just showing you. So this is called QROM, or quantum read-only memory, and it's essentially a way of loading binary data into quantum computers. And it actually has the same form as the circuit I just showed you, except the U's are just products of how the axis. So they're just a bunch of NOT gates. And this, the reason why I talk about this is because this is also a very common primitive, and it's actually used in quite a lot of advanced ways that people do the compare step as well. So initially I thought about this only doing the select step, and I realized this is part of the compare step, so it's kind of talking a bit about it. So to kind of motivate this talk, I'm going to show you a scary plot, which is not really shown on our screen. Essentially, it's the x-axis is a log, is the runtime in seconds of a quantum algorithm on a log scale. So this is the year, and this is an hour. And the y-axis is number of physical qubits, and it's also a log scale, with this being 1 million and this being 100 million. So this is a very scary plot. This plot says, for this region of quantum chemistry, this quantum chemistry algorithm, they resource systems for. It takes, sort of on the order of years with, millions of physical qubits, even when you assume like very good, like gate times and things for your physical qubits.
Whose estimates are these?
So this is from 2 years ago. It's a Microsoft paper. It's called Assessing Requirements to Scale Practical Quantum Advantage. I don't think even at the time all of these examples were necessarily like the full state of the art. I mean, I think even doing that for just one of these applications would be a lot of work. But I think they are sort of like a reasonably good attempt at trying to figure out how you would compile these algorithms onto like Torrent architecture. So people obviously have been trying to improve these, and things move quite quickly. Even in the last 2 years since this paper came out, I'm sure there are plenty of improvements that could be. You could write another paper which just has this but better version of the plot. But I think that there are some kinds of optimizations to quantum algorithms that people don't think about them. So usually when people are trying to think, oh, how can we improve this quantum algorithm? They think, how can I improve the gate count? How can I improve the T count? And that's the like, when in the abstract they say, we reduce the T count by an order of magnitude. But that's not necessarily the only thing that you need to think about. And so that's why in this talk I'm going to be talking a little bit about parallelization. So how can we, and I'm sort of defining parallelization as how can we design circuits to trade off space for time in an as efficient way as possible. So there are some kind of standard ways you could think about parallelizing quantum algorithms. The first one is just to run multiple quantum computers independently. Pretty much every quantum algorithm is going to involve some kind of sampling or probability of failure. So rather than just having one computer and running it many times, you run several simultaneously independently. One of the sort of issues that sort of presents itself when you try to think about parallelizing algorithms for quantum computers is that it's the thing that makes parallelization so easy on classical computers, which is that you can just copy data and send it wherever you like, even to multiple other processes that will do work and then send you back the results. So we can't copy data because there's no cloning theorem, but we can do some things that kind of feel a bit like copying, even though they're not actually copying any information. We can kind of spread out information over a larger number of qubits. Yeah. So this kind of fan-out operation is kind of like a basis-dependent copy. It takes information like kind of in the computational basis, and it spreads out over a series of registers. So a circuit diagram. So this kind of multi-target controlled knot is what people usually call a fan-out operation. And each one of these lines is the whole register of qubits. And for unitaries that act nicely on a computational basis, we can do them all in parallel like this. I'm not sure exactly what like the rigorous definition of acts nicely on a computational basis is, but a thing that I think covers everything that I've been able to think of so far is that they act in a block diagonal form in this basis, and all the blocks don't, intersect with each other.
Which big block diagram? I mean, if you've got the whole of the set that's A, then
right, yes. So yeah, if I'm only thinking about the action on this register,
yeah.
Then I think about the U's, they're all block diagonal, and then if I do them simultaneously like this, the blocks
okay.
don't they don't interfere with each other, so it all goes through this. But there may be things that don't fit that also work. Okay, but what are all these kind of standard methods of parallelization? Because they both have the same scaling in terms of space-time trade-offs, right? They both have a linear scaling. If you want to run multiple quantum computers independently, then if you run two, then it speeds go up twice as much for double the space. And the same with that. So it is actually possible to take the select algorithm we showed earlier and and just use fan out, right? We can just fan out the whole thing, and get and parallelize it that way. And the reason for that is because of those like multi-controlled things, multi-controlled on our partition register, which act nicely in the computational cases. But it's not particularly scalable because in order to speed it up 10 times, we need a quantum computer 10 times as big. So can we do better than that? I'm going to try and argue the answer yes. So what's a kind of another obvious like what is another set of operations that can also obviously be parallelized? It's when gates act on different qubits, right? They're obviously on the same time. And so it's also true that if you have some sequence of unitaries that can be transformed onto gates that only act on single qubits, then you can also do those transformations, act on them in parallel, and then transform back. So that's the idea. In the case where the unitaries are not Hamiltonian are Tauries, which is a reasonably common situation, we can do Clifford transformations to transform these terms into single qubit Tauries. So the circuit looks like this. We have some big Clifford unitary U that does this transform. It transforms all of our Paulis in a set into these single qubit Paulis. And then on the top, the coefficient register, which I've now called alpha, and I think I called it A earlier, I've just done fan on that. And the reason for that is that this register is typically very small in comparison to the other registers, so it's not that much of it.
And that Clifford's effectively taking whatever Pauli string you've got and just rotating it so that it's Z with a whole lot of I's effectively.
Yeah. So if we can find sets of terms that we can transform like this, and we can also find the transformations, then we can apply n-term parallel. We can only apply one. And so what? And all these extra operations are Clifford. So we haven't increased the T count of the algorithm. We're trying to parallelize it without introducing too much extra. So what are the sets? Sorry. So so what are the sets that we can actually parallelize? So in order to diagonalize this set of Pauli terms, we need two conditions. We need firstly that they all commute with each other. These conditions are not surprising because they should also be satisfied by the thing that the Paulis are transformed into, i.e. the single qubit Paulis. So they need to all commute with each other, and we can determine commuting sets of Paulis using some methods that people have already talked about in literature by thinking about graphs. So we produce a graph where every vertex is a term in the Hamiltonian, and every edge is between terms that commute with each other. And then, in order to find these sets, we want to find cliques. So we try and find a clique color of this Hamiltonian graph. This is an empty hard problem, but we do the best we can.
The number of terms of the Hamiltonian is only quadratic, quartic in the size of the thing. So necessarily so.
Well, it's not completely. It's a tractable problem. When I tried to actually use some existing like graph libraries in Python to do this, they weren't fast enough. So I had to start doing better. Okay, and the other condition is that you need linear independence. So if you multiply any terms in a set together, they need to not produce any of the other terms. So from a group, and once we've got the group, we can also get the Clifford transformation. These Clifford transformations can be represented as like a 2n by 2n binary matrix. And there exists code in libraries that I can literally put in the Pauli terms and it will just spit out this matrix, which was very convenient. Okay, so we know what the sets are, and we also know what the transformation. But this hasn't completely solved because we, despite the fact that these U's and these fan outs contain no T gates, they're still not free. And in order for us to actually get any speed up, we need to be able to do the U's sufficiently fast that we actually still get a saving. So they need to be less than linearly deep. And there's, I believe this is the state of the art, is that in the worst case, you need linear depth to compile Clifford gates to only single and 2 qubit gates. So this is where the sort of other component, this is where it comes in, where we can also use measurements, and we can do them much faster if we use measurements. So this is where adaptive comes in. Adaptive circuits means that we do measurements and then we do other operations that condition on the output. Okay, and this is almost entirely based on previous work. I just added one little thing on the end to make it effect. So Clifford circuits can be put into a canonical form, which has been known for like 20 years, involving multiple layers, each of which only contain one type of gate. So, for example, in 2004, this compilation was provided. So, where H is a layer of only having gates, P is a layer of only phase gates, which we call, I guess, we call S gates today. And C is a layer consisting of only C knots. So these H and P layers are kind of trivial; they're just single qubit gates. But the C layers could be what's going to be the depth of our algorithm. They could potentially be very.
The C knots would be just one C knot or multiply controlled, multiply acting C knots.
No, they're single control, but they could be any pattern of them, any complicated pattern. Yeah, they're Clifford, so they're single. Yes, but it turns out that previous work shows that you can actually do these CMOS stages in constant depth, provided you have some resource states that you can use up. So this is work by Zheng et al. In 2018. And in that work, they show that the circuit, although it doesn't appear in their work, but I figured out what it should look like. It looks like this. So you have these two resource states, omega 1 and omega 2, and you do a bunch of entangling gates with this psi register that is the thing you want to apply to Clifford to. You do a bunch of measurements, and then you do some Pauli correction P at the end that depends on all of the measurements you just made. So you need 3n answer qubits in order to do this. And this diagram makes it look like it's 5n, but you could do the omega 1 and omega 2 bits serially. Okay, and these resource states are ground states of CSS codes onto n qubits. So what does that mean? That means, so CSS codes are a common class of quantum error correcting codes. And basically this means that they're +1, these states are +1 eigenstates of a bunch of stabilizers, which all commute with each other. And each stabilizer consists only of a tensor product of x or z's. So each of these states is determined by 2n like strings, which are either only x or z's. And it turns out this is what they are. Omega 1 doesn't, in fact, depend on what the C stage you're doing at all is. And omega 2 has this sector U, which depends on the binary matrix representation of that CMOS stage. And I point out that these states can also be having constant depth. A way of doing that goes like this. You prepare the qubits in each one in the plus state. So now all of your x stabilizers are already in the plus one state. You measure all the z stabilizers, and you randomly get plus or minus 1, and then you fix them just by doing a single layer of x gates. I mean, this is not novel. This is in micro for preparing CSS codes. Okay, so to sort that mini digression, we can do the Cliffords faster. There is a way using 3 and ancilla to do the Cliffords faster. So how much do we actually save when we try to parallelize these elements? Yeah, so we can apply using linearly independent groups of parallels in parallel with like a logarithmic factor increase in qubits. How much speed up does this actually give us Hamiltonians? You know, if I actually were to run some code that takes a Hamiltonian and partitions it into these sets, how well would it do? And I'm going to define a filling factor f, which is the ratio of average group size to the maximum. So f is 1 when you fit n terms into every group, and it's less than 1. You know, if you, it's a half if you only fit n over 2, on average over 2 into group.
And that's in some way measures the complexity of your Hamiltonian.
Yes, yeah,
Loosely.
and also your algorithm that's trying to
be partitioning it.
But yeah, I'm kind of assuming this is just a property of Hamiltonian. So it turns out that for molecular Hamiltonians, or at least for sort of diatomic, mostly diatomic molecules, in Jordan-Wigner encoding, it's about a half. It seems to be about constant at a half, which is nice. Although, I mean, this is only up to 36 qubits, so I can only say empirically up to 36 qubits, it seems to be about a half. But this is nice. It means that for the sort of nitrogen molecule up in the top right, you get like an 18 times reduction in T depth by doing this.
So in this, are you exploiting any form of symmetry inside the, as in, are you just only encoding things that are not zero explicitly in the Hamiltonian?
I only consider the terms that have non-zero coefficients.
Yeah. Because those will, the amount of that changes, the molecules get less symmetric. So you just try
Right, that's a good point.
and so it's not at all clear that you will get a line all the time. That's it. Yeah.
I agree with that. It was this was partly limited by code that exists to produce to actually do the Jordan-Wigner transformations of how fast that. I'd definitely be interested to see to do a more general examination.
Well, you could test it partly by just looking at your diatomics, because your diatomics will have the same symmetries as on board.
Yeah, I suppose if you go from N2,
You could put in a subset of that and see some further damage.
Yeah.
Yeah, but I can say something slightly more concrete for Q1. For Q1, F is approximately 1. And this is because they already commute, and only considering linear independence, it's very easy to find binary strings that are linearly independent from each other. If you have like a large set of binary strings, partitioning them into linearly independent sets is quite easy. I wish I could find a theorem about this. I feel like it should be in some of the discrete mathematics textbook. But all I can tell you is that I have done some numerics, and is that not only is it nearly 1, it actually increases as you increase the number of bits in your strings. Okay, so for at least some practical use cases, we're going to get good speedups. I mean, all I really wanted to show with this was that it didn't decrease as you increase the number of qubits. Yeah. Okay. So parallelization can result in significant depth and T depth reductions. But if we now sort of think about this kind of scheme in like a fault-tolerant architecture level, right? I'm actually trying to run this on a quantum computer. I've reduced the T depth, that's great, but I've not changed the T count. So that means the rate at which I use up T states has greatly increased. And I need more magic state factories to compensate in order to keep the speed. And this could be a problem, but it turns out it's not. And the reason for this is that the relative t-state usage of these circuits is already very low, and it only scales logarithmically with the size of the register. So that actually doesn't kill you. The fact that you do actually have to massively increase the magic statement factories for this particular pass of your algorithm. This particular pass of your algorithm already did not need that many magic state factories.
So I don't have a feeling of what's big or what's small in terms of magic state factories, in terms of, how many do you need for
right
qubit, or wasn't, yeah.
So I think so I have some plot. They don't contain numbers, but I have some plots here. So they don't contain numbers because these kind of things depend on like what kind of errors you want for the whole algorithm things. So, but this gives you an idea of the scaling of how many T factories you need for when your main register is 10 qubits versus when it's 100 qubits. You can see that the fraction of the blue, which is the qubits designated for only producing T states, gets much smaller. Which is why even when we scale it up because we need to produce them way faster, it's still like this. So there's kind of some complexities in thinking about this kind of thing, because I'm kind of thinking about this part of that algorithm in isolation. But of course, there may be another part of the algorithm which needs a much greater rate of T-states anyway, so you wouldn't need to increase it at all. But for now, I'm just going to think about this tiny part in isolation. Okay, so now we have all the ingredients put together. What is the actual saving from doing this parallelization? Not only in terms of how much time do we save, but how much like space time do we save? Because we should now be able to know how much space we actually need. So this is a plot produced using the same software that produced that scary plot I showed you at the beginning, with some scaling factors, because the way they compile to the surface code means that they actually cannot parallelize things in this way. But once you do that, you find that as you increase n, which is the size of your main register of qubits, your space-time, the ratio of the space-time cost of the parallelized version of the algorithm to the serial version of the algorithm actually decreases. So by the time you've got, and this is the happy bubble, so by the time you've got a few hundred qubits on your main register, not only are you running a few hundred times faster, but you're also using kind of 10 times more efficient than the serial version of that.
So in terms of what you're exploiting to make that happen effectively, you're taking advantage of the ability to entangle parts of the larger parts of space to do your parallelization. So I'm just trying to work out, where's that efficiency coming from?
Right, yeah. So this is what my supervisor said to me when I showed him this. And I think essentially it's because the circuits are very inefficient. The original circuits we were trying to optimize are very inefficient. Because they have a large number of qubits, but essentially they're only putting in like one bit of information. I don't mean a bit, just one piece of information every iteration, and the rest of the qubits are just sitting.
I suppose the T-state usage tells you about how efficient they are, the rate of
I feel like there should be some sort of like conservation of magic or something. There's only so much magic going in.
Yeah.
And we can increase that. So this is kind of coming to this point that I was you just asked me about. So the T rate of these circuits, up to this point, I've been assuming that there's need log many T states per iteration. It turns out you can do some optimizations and reduce that to constant by using these kind of unary iteration circuits where you have those multi-controls, but you sort of iterate between them, looking only at the bits that change. So this is
this is optimizing the ordering of which you is in your ROM effectively.
Yeah, but it doesn't matter. So so you pick a good order. So this paper, it reduces the T complexity, but it kind of demonstrates that, it also demonstrates that this algorithm is kind of inefficient in some way. Regardless of how you scale this up, it's always using t states exactly, I think it's like 4 t states per iteration or something. Another point on QROM is that I earlier assumed that fanning out the coefficient register was fine, which is for the case of like physical Hamiltonians, because I know that there are going to be polynomial many terms, and so it's of log size. But for some QROM in the middle of some other algorithm, that may not be the case. And can we also avoid doing this fact using kind of similar techniques? And it turns out the answer is yes. It turns out you can also use Clifford transformations to kind of change the action of the controls in the control register under most cases, not all cases, in order to also only need a constant factor more qubits for that register as well. So we need a constant factor more qubits for the main register because we need like 3n answer for the Clifford transformations. And we can also reduce the control register to a constant factor with qubits as well. And I have some extra slides for this if you want to talk about it. So that kind of leads me on to the end of my talk. And I think this is kind of an interesting way to think about quantum algorithms. For example, can you take this scheme and try to expand the kinds of terms from parallelize? Can you do things other than Pauli, or I believe you can relax the linear independence condition somewhat by using extra qubits? And what are other good targets for quantum algorithms for parallelization? Right, I kind of pointed out that these select QROM type circuits are good targets. One, because they're so common, and two, because they're so inefficient in terms of using up resources at speed.
Is that just you picking low-hanging fruit at this point?
Or, kind of. I mean, so I think it's a good situation because not many people are trying to solve the problem that's kind of on the slide present in this work, which is we have too many qubits. What do we do with them? And the reason we're trying to solve this problem is because no one in the world has this problem. But think of that. Yeah.
Well, thank you. Are you going to have at some point you're going to need to do controls that. Okay, I'm just thinking about physical connectivity of qubits. At some point, you start needing to have an all-to-all type of communication, or which is not possible on a 2D or even, eventually 3D. Your number of qubits, you start needing enough sort of subsidiary qubits in the middle to communicate between them. And will that limit what you can do effectively at some point then?
Yes. So yeah, something that I didn't consider at all in this work is like how you would route this on a 2D architecture or something. I mean, you could imagine something like you have all of these control registers and you just sort of fit them around the outside of your main register and they all go. But yes, I think you will eventually be limited by routing, either in the sense that there are clashes and you need to wait, or you need extra qubits for routing space.
But I suppose you don't need to go all the way to full optimization. You can, get to a halfway house where it's feasible, but not fully optimized.
Right. Yeah. I think this is kind of a interesting design point for quantum algorithms. Like, I feel they should be designed so that you can use what resources you have, right? This uses more qubits than the initial version of the scheme, and you may not have enough qubits to go the whole way, but you can use as many as you have, or as many as routing will reasonably allow you to use.
Now, how much did the classical pre-computation take?
So it's a good question. I mean, it's definitely not trivial, but it's also not. It's definitely efficient. So the sort of code I was using to try to produce that, for example, that plot of filling factors for chemistry components. Some of the larger ones took like maybe an hour, I think, to run, and that's only 36 qubits. But I mean, that was.
You think the scaling of it is like reasonable?
I think the scaling rate is reasonable, and I also think you could do smart things that I did not do. Like you could use symmetries about molecules, for example.
Yeah.
Yeah, mine was basically a brute force.
And once you've got your connectivity, you can change the numbers effectively. I mean, you change your omegas or whatever they are. I mean,
Right, yeah.
the case for a molecule is you change the bond length, fine. The individual numbers change, but the pattern does.
Right, yeah. So it doesn't depend.
Yeah.
Can we go back to the Clifford?
Which,
Really test it.
it looks slightly better on mine. This text in general, or
No, the one with the circuits, there's a few single qubits,
Yeah.
a separate so essentially, can I take it as that you're trying to decompose some of it, I think from say qubit 0, 1 to the n into some like n single qubit. So that they can be graphics.
yes, I'm taking n operators that act on potentially all of those qubits and transforming them into ones that only act on those single qubits. Yes.
Then can this step, for example, small n, can this step be done faster? Because it reminds me of that take back in the just level in DMRG. Say you have a nearest neighbor term, which is 4 matrix in qubits. You somehow do a single variable composition and decompose it into a linear combination of 01, 10, 0, 2. But I guess the sum here would be a problem in the box. Yeah, I'm just.
So maybe there could be something like that, but I think it would probably. My kind of feeling is no, because what this circuit hides is that I'm actually doing lots of these, right? I'm doing lots of these in sequence. I'm doing this, and then there's another thing that looks just like with different U's next to it. So it feels
only includes, say, k qubits, some so-called qubits. Or does the U apply all the qubits?
So you potentially apply to all of the qubits. Yeah.
Okay.
Yeah.
Oh, yeah.
Linear sum of operators can't always be universe. In this, you're getting these little subsets.
Yeah. So you're picking a bunch of like the biggest subsets you can find that you can do this with, and then just see and then just looping through.
Yeah, the rest of them you just apply as they were before.
Yeah, I mean you can.
And essentially all the rest parts of this presentation behind this slide is all about how do you find a U.
Yeah, well, quite a lot of how you find and perform this U. Yeah. And so the U is not the U is not free. It is constant depth, but there will be some size of grouping where it's just not worth applying a U, and you should just apply it.
So something you sometimes have to do is apply an operation that then applies its inverse and things like that. In this, let's say you needed to apply to do that in this case. Can you get any? Is there anything you can reuse in that? You reuse the computation about your grouping. Is there more you can reuse?
I mean, there's a very small optimization you can do where if you're about to do another U here, you can just combine these together. And so that halves your cost, halves the number of times you need to do these Clifford circuits. Yeah.
Because inside there, you've got a whole load of states that are being thrown away and things like that. And I just want sort of under that hood, is there an optimization? I don't have a feeling for that. Yeah.
No, neither do I. But there are some. I don't necessarily believe that this way that I'm doing it, but it is like the best way that could exist. It, in some ways, feels like, I don't know. In some ways, feels funky, and also it doesn't depend on what Clifford transformation you're doing. Right? It's always the same. It's always the same loss. There are ways that you could produce schemes that there are schemes that do a similar kind of thing, but where the cost depends on your circuit, so it could be less. But simple things. Oh, and for the QROM version of this, the use only contains CNOTs, so you need to do one CNOT stage rather than 3.
Between your multiple applications of this sub, do you have to measure?
So the subunit contains measurements.
Yeah. Okay. So yeah. Okay. Yeah. Because you have to kind of collapse each sum of subsets of unitaries. I say that loosely.
Would you have to do those measurements? Yes, you do, because you have to correct. You have to measure and then do.
You have to correct.
Yeah, you have to.
So you only measure. How many times do you measure? Just once.
3 times.
3 times.
Yeah.
Because you've got to measure the all of the answers.
Well, so yeah, you measure all of the ancillas, and for each. Oh, okay, so yeah, so it's 3 times. I mean, it depends how many qubits you use, because you can use slightly more and get fewer, but it's about 3 times, right? You need to prepare those 2 resource states, and then you need to use them, and you need to do that 3 times because the best canonical form that exists involves 3 single stages. So you need to do 9 rounds of measurements in the cheapest possible version of this, which is not time. And then there are some architectures where measurements are really slow.